Hey there, calculators. We are back for the second part of section 3.9, where we are specifically going to talk about logarithmic functions. We had just talked about the derivative, I should say, of exponential functions and how that looks. And there's a little bit about that up here in our notes, and I'm talking specifically about this area, where we see that the derivative of a to the x is a to the x times the natural log of a, that base. And we talk about domains, and we also talk about, when we were seeing where logs come from, a log is just the inverse function, or in other words, it's the function that is reflected over y equals x on the coordinate plane. So here, in these two pictures, you see the blue function, which is the exponential function. So for instance, over here it is y equals 2 to the x, and we show that the reflected function is y equals log base 2 of x. And over on the right side, I used just a fractional, a base between 0 and 1 of 1/2 to show you that it kind of looks different, but it still maintains that reflection over y equals x. And that's all that is. What we are going to do down below is we are going to kind of algebraically prove the derivative rule for logarithms, and you're going to see that here. And just a reminder that the log base anything of x is the same as saying x is equal to a to the y power. So we are going to use that to our advantage. I'm going to rewrite x equals a to the y power. I am going to take the derivative with respect to x of both sides. And that might seem a little strange, but hopefully in a minute you're going to see where I'm going with this. Because I'm taking the derivative with respect to x of x over here, because these variables match, this derivative is just going to be 1. And when I take the derivative of a to the y, there's a little more to it than that. But remember, we know, and it's in the rule up here if you need to see it, that is just a to the y times the natural log of a. But because we decided to use a different variable, we need to represent that chain rule with dy dx. And that is actually a really good thing for us because we are looking to find out what dy dx actually is. And so algebraically, there's only one more step here. I'm just going to divide both sides by a to the y times the natural log of a. Natural log of a. And I get, after all that, dy dx is equal to 1 over a to the y times the natural log of a. But even cooler than that is that a to the y is just x. So I can make, and that's usually mathematicians' goals, is just to make things simpler, believe it or not. We can say dy dx is equal to 1 over x times the natural log of a. Now, I am going to be perfectly honest with you. We don't use this derivative a whole lot. The derivative that we use a whole lot is the derivative of the natural log of x. We use that all the time, and you're going to see that from this point forward throughout the entire course. And you might think that's a different rule or a separate rule, and it's not, because remember that the natural log of x is just the same as the log base e of x. And so now we are going to apply our new derivative rule to that to see if anything different happens when we use that special base of e. Well, here we go. That means we're going to go using our new rule, 1 over x times the natural log of that base, which is e. But wait a second. The natural log of e is just 1. So the real power in this lesson is saying the derivative of the natural log of x is just 1 over x. And that, my friends, will be used all the time in calculus, especially the calculus you're doing in this course. And then if you choose to take Calc 2 in college or If you choose to take Calc BC and take that second semester of calculus, you will see this all the time. So those are the two rules we're going to roll with through the rest of the problems on this page or these pages today. I'm going to kind of just go through each problem. So if you kind of think you have it and you want to skip forward, by all means. If you feel like you don't have it and you want to go slower, feel free to adjust the speed if you have that capability, or pause and try a problem and then come back and see what I've done. So let's kind of move down into these problems here. I'm going to leave those rules up front and center so you can see where my work is coming from. And letter A is actually kind of fun because it's not just the derivative of the natural log, it's also got some chain rule and power rule attached to it. So here we go. dy over dx is equal to, this is first and foremost a power rule problem. So 2 times the natural log of x to the first power. We're not going to write that because it's just the same thing. But because we don't have just a simple x in here, because we have an entire function, we need to take the derivative of that function. And we just learned that the derivative of the natural log of x is 1 over x. And so there's a couple of different ways we can write this algebraically. I would probably just go here and say dy dx is equal to 2 over x times the natural log of x. And that is all you need to do. Letter B is even faster, but what might trip you up in letter B is wondering what the base is for the log. And because it's not written there, and that's intentional, that wasn't a typo. But just remember, if we ever have a log without a base written, it is assumed that the base is 10. So once you know that, this is just a very fast problem, dy dx. The 1/2 is a constant multiple, so that can just come out front. And from there, it is 1 over x times the natural log of 10. We can multiply those fractions together and make one clean expression, 1 over 2x times the natural log of, not x, I'm sorry, but 10. Okay. Letter C, we've got a natural log of x and a natural log of y, but at this point in the unit, you are implicit differentiation pros, and that's exactly what we're going to do. We're going to take the derivative of both sides with respect to x. So the derivative of the natural log of x is 1 over x. The derivative of the natural log of y is 1 over y, but don't forget to employ the chain rule because it's a different variable than what we're taking the derivative with respect to. On the right side, the derivative of 2x is just 2. And then we just need to do some algebraic work to get dy dx by itself, and we're going to do that. And so here we go. We're going to take away 1 over x from both sides. And you would write that like this. And then all we have to do to get dy dx by itself is just to multiply through by y. So dy dx is equal to 2y minus y times 1 over x is y over x. And while that looks like a really weird derivative, it kind of is, it is totally legitimate and okay to write it that way, and that's how we're going to keep it. All right, and finally, letter D, we are going to take this derivative. So it's a log with base 2. So when I say dy dx, I'm going to use my logarithm rule and say 1 over. Now, normally we would say x times the log or natural log of 2, but we're not just taking the log of x, we are taking the log of x cubed. So I need to take that times the natural log of 2, and then chain rule, take the derivative of x to the third, which is 3x squared. Now, algebraically, some interesting things are going to happen because when I multiply those two expressions together, 3x squared is going to move into the numerator, and then I've got some factors of x canceling out in the numerator and denominator. So when I do all of that, I get dy dx is equal to 3 over x times the natural log of 2. And there we go. We had a lot of things cancel there, so be careful and make sure you understand where that's happening. If you have a question there, make sure you put it in the comments. And that's how we'll leave it with these 4, I would say, basic to medium problems. Now, this next problem, this can you do it? It looks really gross. It looks like something we might not be able to do. But what I'm going to show you here is the first step, and then I'm going to leave the rest up to you. We'll post a key eventually so you can see the final answer. You might want to bring this to your teacher the next day in class after you watch it. But here is the interesting piece, and take a look at this. We have y equals the natural log of all this garbage, and it really feels like a lot of just trash because there's so much here. But because the log is already there, watch what I can do. I'm not even taking the derivative yet. I'm just going to use my log expressions to rewrite this whole massive fraction as 3 relatively simple logs. The natural log of 2x minus 1 to the 3rd power plus the natural log of 2x to the 4th plus 1 to the 1/2 power minus the natural log of x. And I can do that because the natural log rules, or any logarithm rules, say that if I have a product inside of a log, I can separate those out into an addition problem. And if I have a quotient inside of a log, I can make that a subtraction problem. And we have all those things here. Furthermore, we can make this even simpler by bringing these exponents down in front, which is another logarithmic rule. 3 times the natural log of 2x minus 1 plus 1/2 times the natural log of 2x to the 4th plus 1 minus natural log of x. I am going to let you take it from there. Those should be 3 relatively quick derivatives for you to take. And I have just one more problem for you to try out. Maybe 2. We'll see. Here we go. Here is where things get a little tricky. And this is the one I wanted to spend the most time on. The problem we just looked at was made easier because there was a natural log involved, and it let us split apart the pieces of that really, really gross rational expression. Here is another really gross rational expression, but we don't have the benefit of the log. Here's the cool thing, though. As mathematicians, we can just add that log in as long as we do it in an algebraically sound way. So for instance, what if I just took the natural log of both sides? And that's what I'm going to do. And maybe you see where I'm going with this. Maybe you don't, and that's okay too. Because now that the log is there, I know the natural log of y on the left side might be giving you trouble. But now that the natural log is there on the right side, we can do something like this. Natural log of x squared plus the natural log of 5x plus 1 to the 1/2 minus the natural log of 3x minus 2 to the 3rd. And again, the natural log of y we'll deal with momentarily. But I'm going to make this even simpler by dealing with these exponents. 2 natural log of x plus 1/2 natural log of 5x plus 1 minus 3 times the natural log of 3x minus 2. And just remember, that is happening because I can move these exponents down in front. And that's what I am doing. Now we can start doing some work. We are going to take the derivative with respect to x of both sides. And if you would rather just write parentheses and that little apostrophe or the tick mark, that is the same thing. So what I have is an implicit differentiation on the left. The derivative of the natural log of y is 1 over y, but because the y doesn't match the x in the derivative operator, I need to actually represent that with the chain rule. The right side is all in terms of x, so it's a party. Here we go. 2 derivative of the natural log of x is just 1 over x plus 1 half. 1 over 5x plus 1 times the derivative of 5x plus 1 minus 3 times 1 over 3x minus 2 times the derivative of 3x minus 2. So now I have 1 over y times dy dx is equal to 2 over x plus 5 over 10x plus 1 minus 9 over 3x minus 2. Now keep in mind what I was trying to find. This is where it gets a little tricky. I am trying to find y prime. Y prime is another way of representing dy dx. And I am almost there. I am almost done. All I need to do, and maybe you're saying it along with me, is multiply through by y. So dy dx is equal to y times this whole mess. Now, if this was a multiple choice test or multiple choice question on the AP test, it would be a little more complicated because this would not be a choice. What they would do is they would go way back up to the original problem and they would substitute in the original expression for y. So again, not great here, but we can do it. Here we go. dy dx equals x squared and now we have a derivative completely in terms of x, which is what they're wanting. Fair warning, the people on the College Board, the AP people, might be a little extra devious and make you multiply that out into a trinomial, and that's something you can do algebraically. I believe in you. But in terms of our work today, that is enough to get you started on the problem set. Down here at the bottom, I do just have a few steps for using logarithmic differentiation, which is what we did on this problem. This is an example of logarithmic differentiation. And you can read those steps there, and maybe that will help you a little bit. And maybe just seeing my example might be more helpful. Whatever works for you, you have this at your disposal. Thank you for your hard work today and your time. I will see you next time when we are talking about 3.11, which is all about related rates. See you then.